I'm Zach Collin.
And Justin Thompson, and this is our project for the MAE 535 demo project.
For electroradiological fluids. Introduction. An ER fluid is a fluid that changes its flow characteristics or viscosity in the presence of a high voltage, low current electric field. This shift in viscosity is instantaneous with the application of the electric field. And if the strength of this electric field is sufficient, the fluid behaves much like a solid. That's exactly what we're going to be demonstrating today. The principle of that fluid acting like a solid is actually can be applied to a valve without moving parts. Other applications include vibration isolators, tunable dampeners, non-slip fluid clutches. Other interesting applications include dynamic braking for stationary bikes and other exercise equipment, and milk chocolate processing. Molten milk chocolate itself is an electroradiological fluid, and that can be used in its processing. There's three theories behind ER fluid behavior. The first is fibrillation structure formation. This is the formation of chains along the electric field lines, increasing apparent viscosity. There's also deformation of double layer and overlap. This is illustrated below. And the third, alignment of discrete particles. I'm going to be turning over the next few slides to Justin.
Alright, this here is our setup. What you've got here is the, essentially we've set up a vat in which we'll pour liquid. Once the liquid goes down that vat, we've got two electrodes set up on top of, that are actually shielded behind some plastic. The next slide is actually going to show you a close-up view of those two electrodes. This is looking at a cross-section across the electrodes. We've got a positive and a negative electrode, and using Gauss's law, there's going to be an electric field formed right in the center here that should be fairly uniform, because as long as you look at the center of those plates, you can, as long as they're close enough, you can imagine that they would simulate an infinitely large sheet. So once we set up that uniform electric field, we figured out how much voltage it took to actually calculate or to actually stop the fluid from flowing through our valve. To get the viscosity high enough and overcome the shear caused by the head pressure, we had to apply 3,600 volts and across the two plates across a 4 millimeter gap. This came out to be 900 volts per millimeter, which seems to be a fairly strong field, but seems to be in line with what we found in electroradiological fluid literature. Our particular recipe, we chose to use dolomitic lime, just like you would put in your yard. We also chose to use olive oil, just like you'd use in your kitchen, and a small amount of water. Added the dolomitic lime to pre-moisten the lime prior to mixing. We used about 40% volume of lime and 60% volume of olive oil. Some other potential ER fluids that you could be made from common household items include just plain molten milk chocolate, mineral oil, and gelatin, and there are numerous others that can be found in literature. Now we're going to go into our demo. Alright. First I'm going to add the power from our power source.
And you can notice the viscosity of our electroradiological fluid. It's fairly low, so it's got good flow characteristics, and behaves similar to water. I'm going to go ahead and add that into our demonstration device.
And right now we have the high voltage power supply set to 0. We'll take just a second for the fluid to start going through that 4 millimeter gap and make it to the bottom of that gap, and then you'll start to see flow coming through the bottom. We actually had to tamper with this mixture quite a bit to, even though we say 40 and 60% by volume, it actually took quite a bit of tampering. Once we got that base set, mixing in a little bit of lime or a little bit of olive oil to get it just right.
We also had some trouble with short-circuiting the circuit, and we had to remove our fasteners and replace it with non-conducting glue.
Yeah, we tried to use nylon screws, but we found that the fluid would find its way into the thread of the screw and short across. Hence, we have the thin plastic layer to prevent the conduction through the fluid itself.
You can notice a nice laminar flow. It's rather slow, but it does show nice flow characteristics.
So now we're going to go ahead and turn on the power supply up to approximately 3600 volts. And you should notice that the fluid stops flowing. And actually you can see it hanging there.
And even though it's dripped down past the opening, it's suspended and won't actually fall.
And I think that shows it. Now we're going to go ahead and take the power back down, and you should see that it should start flowing again. As we watch it flow, we're also going to talk about some of the limitations of a electrorheological fluid.
MR fluids and ER fluids share some similar design limitations, one of which is sedimentations of the fluid. We actually saw this in the construction of our demo. We mixed together our ER fluid early last week and then left it sitting around and then found out that it was completely useless when we came back to it 5 or 6 days later.
Also, as we mentioned earlier in our presentation, we did have a problem of shorting. This is very important ER fluids because you have to deal with the dielectric breakdown strength of the fluid, which is something you don't have to worry about with an MR fluid. You also have to worry about the electric insulation of the electrodes from the fluid and also from the container containing the fluid, quite possibly. You also have to worry about the particular electrode configuration. We chose 2 parallel plates in our valve in order to show that, in order to achieve our electric field.
Some of these reasons are why MR fluids have much more application in industry and manufacturing than ER fluids.
I'm going to turn the power supply back on again, and hopefully you'll see this stop flowing one more time. And that concludes the presentation for our electrorheological fluids for the MAE 535, summer of '09.